Hi Year 10, let's have a little look at your written section of your mock or your end of year exam. So question 1 shows a sealed weather balloon which is stationary in still air. They don't tell you this for no reason, so make sure that you're paying attention to the little words. It says state whether the overall density of the balloon and its instruments is greater than, less than or the same as the density of the surrounding air. So we know that convection currents are set up when there's a different density of gas. Okay, so if we have a high density gas and a low density gas, this is going to fall to displace the less dense air. So the fact that it is stationary must mean that the density of the air inside the balloon and outside of the balloon is the same. So you just get 1 mark for saying same. In B it says at night the gas inside the balloon cools. The pressure of the air outside the balloon remains the same. State whether the balloon rises, falls or remains stationary. So if it cools down, that's the crucial bit, it is going to lose kinetic energy. So it's not going to move around as much. It's going to take up less space. Okay, so therefore the volume is going to decrease. That's going to make it more closely packed. That makes it more dense. So now what we've got is more dense air inside the balloon and less dense outside. So the balloon is going to fall. And we just have to give what we just said as our explanation. So the volume of the air inside the balloon decreases. That gets you 1 mark. And then secondly, this causes the density inside to increase. Okay, and that's worth the 2nd mark. So 1 for talking about the volume decreasing, 1 for talking about the density increasing. Okay, so then it's the same question but a different topic. It's going to start talking about motion graphs. An object is released from the balloon. It starts at rest, which we know means not moving, so we've got 0 meters per second. So here's our object. It eventually reaches a constant speed, so therefore it obviously speeds up. So it has its weight acting down. Initially it's at rest, so we start at 0, 0. So when time is 0, we have no speed. It's going to fall under gravity, so it's going to accelerate due to gravity, so that's going to be 10 meters per second squared initially. But as it does that, it's starting to fall through air, and the air is going to exert an upwards force, a resistive force, air resistance up. Okay, so therefore the overall force is going to decrease. Now we know that acceleration is force per unit mass. So if the force decreases, then the acceleration also decreases. Okay, so initially we show it accelerating at 10 meters per second squared, but as it falls through more air per second, as it's speeding up, we know that the acceleration is going to decrease. Okay, and it's going to decrease until it reaches a constant speed. So in an exam, get your ruler out for this bit and make sure it looks horizontal, because they're going to be checking for that. Okay, so at the point where it reaches a constant speed, we want to see this. Okay, try and keep it as smooth as possible. So you get 1 mark for recognising that it needs to start at 0, 0. You get 1 mark for recognising that when it reaches a constant speed, I need a horizontal line. And you get 1 mark for knowing that the gradient of a speed-time graph is change in speed over time, which is acceleration. And we know that the acceleration is decreasing, okay, because there's less resultant force because air resistance has gone up. Okay, so if the gradient is acceleration and acceleration is decreasing, it needs to become less steep. Okay, so you get 1 for showing it getting less steep. Then it says state the values of the initial acceleration and the final acceleration of the object. Well, initially there is no air that is hitting the object when it's at the very start of its fall. So it's falling under gravity, and we know that acceleration due to gravity is 10. And we know that its final acceleration has to be 0 because it's not changing speed. make sure you get your unit right for acceleration, please. Meters per second squared. Okay, question 2. So we've got a wooden trolley of mass 1.2 kilograms at rest. So again, 0 meters per second on the rough surface of a bench. A ball of mass 0.52 grams travels horizontally towards the trolley. It embeds, so sticks to the wood of the trolley, and it moves with an initial speed when it gets hit of 0.065 meters per second. So calculate the impulse. We know that impulse is change in momentum. Okay, so that's going to be the final momentum, mv, minus the initial momentum, mu, which is equal to m brackets v take u, because I factorised that. So I'm looking at the impulse of the trolley, so the change in momentum of the trolley. So I need the mass of the trolley. So I have 1.2 kilograms multiplied by the change in speed. So its final speed or velocity was 0.065 minus its initial, which is 0 because it tells us it's at rest. And when I do that on my calculator, I get 0.078 kilogram meters per second. Okay, because it's a mass value multiplied by a velocity value. Then it asks for the speed of the ball as it hits the trolley. So, the ball striking the trolley is what has caused the trolley's momentum to change. Okay, now momentum has to be conserved in total. So if the trolley has increased in momentum by this much, then the ball has to have decreased in momentum by this much. Okay, so we've got impulse is change in momentum. And we know then that the impulse value, if it was gained by this much by the trolley, it was lost by that much by the ball. And we know that momentum comes from mass multiplied by velocity. So we're going to take the mass of the ball, but notice that that was given in grams, so I have to convert that to kilograms for this to work. Okay, multiplied by the change in velocity. So delta V is 0.078 over 0.52 times 10 to the minus 3, and when I do that on the calculator, I get 150 meters per second. Okay, now I know that the change in velocity of the ball is the original speed as it hits the trolley, because relative to the trolley, once it becomes embedded, it's moving with the same speed as the trolley, which is a 0 meter per second velocity. Okay, they are stationary relative to each other at the end. So therefore the change in velocity must be the initial velocity of the ball. So then in B it says, as the trolley moves across the rough surface, it slows down and stops. Explain in terms of the work done, so I need to see the phrase work done in your answer, the energy change that takes place as the trolley slows down. Okay, so we're going to firstly get started with our work done. Work is done by the trolley against the friction. Okay, so what that means is because there's friction, the trolley has to do work, it has to lose some energy, okay, it has to transfer some energy, would be a better way of saying that. So that is worth 1 mark. Now work done is energy transferred, so if the trolley has done work and transferred energy, we know that its kinetic energy that it had to start with was kinetic energy, it was moving. It's slowing down due to friction, right? So we're just going to say kinetic energy decreases for the second mark. So now I've got the energy change that has taken place. This type of energy has changed, it has decreases. But we don't just have energy disappearing, it has to be transferred to another form. So the third mark is saying where that energy is transferred to. Now obviously when there's friction, heat is generated, okay? So this is transferred to thermal energy. You could say heat energy, I would give you the mark for that. Okay, so that's your 3 marks for that question. Okay, question 3. A solar panel receives energy from the sun at a rate of 5 kilowatts. Again, before I start, I'm going to write that into standard units. That's 5,000 watts. Thermal energy is transferred from the solar panel with an efficiency of 20%. I'm going to write my efficiency equation. It's the useful energy output divided by the total energy input, and then to turn that into a fraction, I multiply by to a percentage. Sorry, I multiply that by 100. Cold water of mass 15 kilograms enters the solar panel every hour. The specific heat capacity of the water is 4,200 joules per kilogram degree Celsius. Calculate the temperature increase of the water. So I know that 5,000 watts, which is 5,000 joules per second, is reaching the solar panel. Okay, I'm going to draw a little diagram here just to make sure we're clear. We've got 5,000 joules per second of thermal energy reaching our solar panel. Only 20% of that, so a fifth, is going to be able to be transferred to the water. Okay, and so we're going to then multiply this by 0.2 for 20% to find how much of the energy can be transferred to water. Okay, now because this is a fifth of 5,000, it's just 1,000 joules per second of the original 5,000 can be transferred to the water. Okay. Every hour, 15 kilograms of water can enter the solar panel. 1 hour is 60 minutes worth of 60 seconds. Okay, so that's 3,600 seconds. If I know that in each second 1,000 joules is transferred, then I can say the total energy gained by the 15 kilograms of water is going to be 1,000 joules per second for 3,600 seconds. Okay, so I get a total input energy of this number. Okay, now this is thermal energy, so in our specific heat capacity equation, that's Q. Okay, that's why this is worth 4 marks, because there's a lot to think about here. I've actually run out of space as well, so let's just draw a little box so we don't get lost. Okay, so our specific heat capacity equation is Q is mc delta T. It asks for the temperature increase of the water, so I'm going to rearrange and say delta T is equal to Q divided by mc. I'm trying to find this. I've just worked out the total amount of energy that has been given to the 15 kilograms of water, so I say delta T is equal to my energy divided by my mass, which was 15 kilograms, multiplied by its specific heat capacity value, which is 4,200. When I do that sum, I'm going to get my temperature increase. So let me just pop that in the calculator. And I get a temperature increase of 57.1. You'll see I'm only going to give that to the nearest degrees Celsius, okay, because I'm not really going to be able to measure that more accurately in reality. Okay. In B it says, state and explain one advantage and one disadvantage of heating the water in a solar panel compared with heating the water in a coal burning boiler. So we're not talking about the advantages and the disadvantages of the coal burning boiler. We're talking about why it's better to use the solar panel to heat the water and why it's worse. Okay, so the clear obvious advantage is that the solar panel is renewable. Or that there's no greenhouse gas emissions from this. Okay, so no pollution. You could have had either of those and that would be fine. Okay, so the explanation of why renewable is an advantage is that we will always be able to heat the water, or that we don't add to global warming. Okay, we're not contributing to global warming. Okay. There are disadvantages though. You could say that it's expensive to install. That would be fine. I would say that actually a more obvious one to choose is that you can't use it at night. Excuse the primary children just walking past. So you can't use it when the sun is not shining. I phrased that terribly actually, because technically the sun is always shining. So let's be careful and say during bad weather or at night. I should have thought about that before I started writing. So that's a disadvantage. And then the explanation is obvious. You want to be able to heat the water whenever you want to heat the water. Okay, so you are restricted as to when you have hot water. Okay. Okay, question 4 then. The kinetic energy of air passing through a wind turbine every minute, again, let's put that in standard units for physics, that's 60 seconds, is 720,000 joules. The electrical output of the turbine is 9 amps at a potential difference of 240 volts. Okay, so, sorry, just pause the video, so sorry if it seems like a weird jump. Unfortunately, you can't complete the question without the extra bit of information that I stapled into your test, because we haven't looked at electricity yet. But basically, in year 11 you will learn that if you multiply the current by the voltage, then you get the power. And when you do that, you get 2160 watts. Which is joules per second, but again remember ours was in minutes, so if I take that number and multiply it by 60 seconds, I know that I get this many joules out, and that's the number that I gave you. So then from there, efficiency is the useful output over the total input multiplied by 100. Okay, so we're going to get 129,600 divided by the total going in. Multiply that by 100, and when I do that, I get 18% efficiency. Okay. Question 5. Figure 2.1 shows a uniform plank AB of length 2 meters suspended from 2 ropes X and Y. The weight is 210 newtons acting from the centre. We know it is a 2 meter plank And because it tells us it's a uniform rod, the mass is distributed evenly, and so therefore we know that this is going to be in the centre of the plank. So this distance from A to here is 1 metre. The force in rope X is P, the force in rope Y is Q. State in terms of P the moment of the force P about B. Okay, so here we know that moment is the force F multiplied by the perpendicular distance. Okay, so the force here is P, and that tells us we can leave it in terms of P. And the perpendicular distance from B to P, so if P is here, at 90 degrees to P is the horizontal, and we're finding the distance to the pivot, which is B, which is 1.5. Okay, so if you literally wrote P times 1.5, you get the mark there. Then it asks you to calculate the moment of W about B. So, if this distance is 1 metre, and this distance has to also be 1 metre, that gets me my perpendicular distance. Okay, so this is 1 metre, and so therefore about B, this is my pivot point, my force times my distance, my perpendicular distance, is the 210 newtons multiplied by 1, because that's your distance to the pivot. So I get 210 Newton meters. Then it asks you to calculate the force P. So let's think about this. We've got an anti-clockwise moment from the weight, and then we have the rope P pulling up around the pivot point. So this one is clockwise, and this one is our anti-clockwise. Okay, it's suspended, so it's not moving, so therefore it's in equilibrium, so I can say that clockwise moments equals anti-clockwise moments. Okay, now I've just worked out that the anti-clockwise moment from the weight is 210, and the clockwise moment I said was 1.5p. Okay, so I can rearrange that and say P must be equal to 210 over 1.5. Okay, and you should get 140 newtons, and that is your answer here. Okay, then it asks for the force Q. Now there's an easy way of doing this, which is that we know that if we have equilibrium, there's no resultant turning force, no resultant moment, but there's also just no resultant force. So for this thing to be suspended and not moving up or down, then all of the upwards forces have to add up to all of the downwards forces. So I know that P plus Q has to equal the weight. Okay, the two forces up have to equal the pull down, otherwise we'd get movement up or down. Okay. Now I know that P is 140 plus Q, which is the unknown, must equal my weight, which is 210. So therefore Q is equal to 210 minus 140. Okay, and when you do that, you will get 70 newtons. Okay. In question 6, it says describe in terms of molecules. So again, I need to make sure I've got the word molecules in my answer. What happens when a liquid evaporates? 4 marks, so 4 distinct points. 1 mark for saying molecules escape from the surface of the liquid. This is just a memory question, really. Okay, so that's 1. The second mark is for saying the faster or higher energy molecules are the ones that escape. Obviously you can combine these two sentences. You can say higher energy, sorry I forgot to put that in, higher energy molecules are the ones that escape from the surface of the liquid. You can combine that into one sentence, that's absolutely fine, you get 2 marks there. Slower or lower energy molecules are left behind. Can't spell today. So, therefore, the 4th mark, the temperature of the liquid decreases because the average kinetic energy, I'm going to put KE because I'm running out of space because I'm trying to write big so that you can see it. So because average kinetic energy of the molecules is now lower. Okay, and that's the 4th mark there. In B, we've got figure 4.1 shows wet clothes drying on a washing line. State 2 changes in the weather that help the wet clothes dry more quickly. So you could say temperature increase. You could say more wind. You could say less clouds. Those would all be okay there. You just need 2 of them. Okay, question 7. So, the wave reaches a barrier. Okay, so we've got a wave, it's reaching a barrier. We can see it passing through a gap. The frequency of the wave is increased to a value many times greater than the value obtained in B. Describe and explain 2 ways in which a diagram representing the wave with a greater frequency would differ from figure 6.2. Okay, so if the frequency has increased, we have more waves passing a point per second. Now each of these vertical lines is a wave front, which shows a peak of a wave. So if we have more passing a point per second, what we know is that we are going to see more compressions and more rarefactions in this area. Okay, so we're going to say, firstly here, more compressions and rarefactions would be seen. Because it's asking about how the diagram would look different. Okay. Then what we need to think about is what happens to the diffraction pattern. Now remember, I showed you on the ripple tank that if you have a wavelength that's very, very short with a big gap, we get very little diffraction happening. Okay, so we don't see it very much. When the wavelength matches the barrier size or the gap size, that's when we see the really clear diffraction pattern. Okay, now if we've increased the frequency, we've decreased the wavelength. Okay, and so now the wavelength is going to be much smaller than the barrier, and so the diffraction will be less. Okay, so we will see less diffraction.
If you like, I can search the web for so we will see.
Sorry about that. Phone no good at physics. Right, so we've got seeing less diffraction or less spreading out. Because it's worth 3 marks, we need to explain why. Okay, so more compressions and rarefactions are seen. Therefore, we see less diffraction because the wavelength will be much smaller than the gap size. Okay, so this bit's worth 1 mark, this bit is worth 1 mark, and this bit. Okay. So question 8, 2 forces. An object is moving in a straight line at a constant speed. A force is applied to the object. State the possible changes in the motion of the object. So there were 4 options and you only needed 2 of them. So you could say speed up or accelerate or slow down. They're all worth the same mark point because they're indicating a change in speed. Okay. You could say the object comes to a stop or to rest. Okay, because it was moving at a constant speed and then a force is applied, so we could stop it. We could also change the direction of the object. Okay.